Howdy. I am recording week 4, a video on Bayesian Belief Networks. Now, this is something that as you see these, you will begin to understand why we're talking about these in enterprise risk. And I apologize for some reason. These slides will not download, so I'm having to do this through the through the shared drive for Google Docs. So anyway, who knows? Bayes Theorem, here's the way to think of it. Think of putting all two words, nodes and arcs. And a node is a circle, and an arc is a connection between circles. So the node is an event. So I say, what's the probability I'm going to have lunch today? And then my second node would be, and if I have lunch, I'm going to go to Applebee's. Or I'm going to go to Johnny Carino's. Or I'm going to get barbecue or something. So it's probabilities built on probabilities. What's the probability I'm going to drive to College Station today? And given that I drive to College Station, what's the probability I'm going to have a traffic jam between Houston and College Station? And given the probability that there's a traffic jam, what's the probability it's due by construction or it's due by a car accident? So it's probabilities based on probabilities. And Bayes' theorem was just that. So it describes the probability of an event based on prior knowledge of conditions that might be related to the event. But there's several different actions we could take. Now, a classic example is testing positive for a disease that occurs 0.1% of the population. So you would say, well, what's the probability of having this disease? And given that you have this disease, what's the probability that you're going to die from it, you're going to do this, you're going to do that? So it takes into account really small populations or really small events that might be those black swan events. So most people assume they have a 100% chance of having a disease. However, you find out that a false positive happens, and then what's the chance you have the disease knowing this? So it's all these probabilities that add up. There's a let's think question in here. You might say, how much effect do you think a 1% chance can have on the probability of a downstream event? This is where the black swan events come in. Low probability, high impact, high consequences. So there's false positives. So what's the probability that you actually have the disease is very small, but the probability that you are told you have the disease higher. This happens actually a lot in cancer. There's certain forms of cancer that all they know is that you have that cancer. And in a very small percentage of those people, that cancer will advance. But they don't know which percentage of people. So they err on the side of caution and they treat everyone with the same chemo and surgery and all of this because they don't know. So the chance of having the disease is 9% or 1 out of 11, right? That's how small but a relevant decision can influence this. So when it says 1 out of 11, it doesn't mean 1 out of 11 people. It goes back to the fact that it's 1 out of the 11 who tested positive for it. So let's go back and make sure I explain this well. The probability of having that disease is 1 in 1,000. But the probability of having a false positive is 11 out of 1,000. So the probability of having it if you are told you have it is actually only 1 out of 11. Now, Bayesian Belief Networks came about in the 70s, 80s, 90s by a brilliant computer scientist, a Turing Award winner named Judea Pearl. J-U-D-A-A-P Pearl, P-E-A-R-L. He used them for what was called causal networks, how things actually look like they possibly impacted other things, right? Because all of life is probability. So finding the root causes and the like. They were also used by terrorism or to detect terrorist events, believe it or not, because if you had that this probability, let's say someone bought ammonium nitrate in a U-Haul, what's the probability they're a farmer? What's the probability you're in this? But they linked it to other events. What's the probability that this person isn't a farmer? What's the probability that he's also done this or this? It sounds kind of goofy, but they would come up with these nodes of information that they could collect automatically, populate these Bayesian belief networks, and try to detect events or groups or things like this that were going to do something nefarious. The reason I bring this up is Mr. Pearl, Dr. Pearl's son, was actually killed by terrorists shortly after 9/11, completely unrelated to his work. He was a Wall Street Journal reporter, Daniel Pearl. He was kidnapped and beheaded. So it was one of life's ironies that Dr. Pearl's work, his entire life, was based on developing mathematics and formulas that, not because of his work, but was used in terrorism network detection, and that his son was killed by that, surely purely because he was a Wall Street Journal reporter in Pakistan and was Jewish. Had nothing to do with father's work. But Judea Pearl is one of the best computer scientists living today because of this work. And this is what I was talking about. Think of the circles and the arcs, the nodes and the arcs. What's the probability this would happen? Now, here's the deal. We're showing you some pretty simple kind of things. But the actual thing is that if you can get, the actual observation is if you can get the data, Bayesian belief networks can be graphs of hundreds of thousands of nodes. I mean, the probabilities of events are very complicated and complex. So we're showing you some simple stuff here. And they have some strengths and weaknesses. They're modeled based on prior events. They can be easily updated. There's this rich mathematics. Remember when I said before, there's three things that we have. We have software, we have hardware, we have advances, and then we have mathematics. And so there's this rich history of mathematics and graphical and the like. So the weaknesses is finding this data, finding the prior events that are actually relevant, right? 9/11 was a watershed event in that planes were used as suicide weapons. Data before that might indicate something was going to happen gets changed for the dynamics. So again, even though this is great mathematics, you can model it, you can update it, everyone can understand it conceptually, it's hard to identify prior events. It's hard to grab that data. And a lot of times the prior events can't really predict the future, but it's still a good technique to use. So again, it's a simple BBN chart. If it's raining, what's the probability that if the dog barks, he's barking because it's raining? I have a dog that has a problem with thunderstorms, right? So if he barks, the question would be, is he barking because he senses a change in the weather, which usually happens, or is he barking because he sees someone walking down the street, right? It's all probabilistic. So as you build these models, you begin to see some of the strengths of the models, but also where the proper applications are. It's not applicable to everything that we want to do, but it's a good tool to have in your kit if someone comes and talks to you and says, hey, I think this problem, a data scientist, I think this needs a Bayesian belief network. You can come back and say, how are we going to get the data from prior events? How are we going to validate that data? And that's my brief introduction. We've got a video on it. I hope this helped. We're looking forward to talking to you in office hours Monday evening.